But I do like the idea of walk-up music for all our program managers during spring review. That would be something fun to keep us energized throughout the week. So I'm John Schmisseur, and in addition to being department chair, I'm also program manager for Aerothermodynamics and Turbulence. One of the themes of my talk today is transforming the present, inventing the future. We try to have a balanced mix of things that have both relevance with the Air Force needs right now in terms of addressing showstoppers and game-changing things for the future, and we'll hopefully cover the full spectrum there. This is a little different than many of us gave talks to the Scientific Advisory Board last week, where we focused on what have we accomplished recently. I'm going to show you some highlights today, but they really are not what we've accomplished. It's where we're going. So a lot of this work is ongoing. We're still waiting to see how things are going to pay off. A lot of these things are in their first year, but this presentation is designed to give you a sense of where are we going as a portfolio and why. So my portfolio exists at the intersection of gas dynamics, thermophysics, and chemistry. And the icon here shows some of the phenomena that we have to address. We've got strong shock waves, excited thermophysical states, some viscous effects. And one of the key challenges is that there are time scales of all these phenomena for very high speed flows occur in the same thing. So we can't separate out thermophysics from kinetic effects. Because the time scales can be of the same order of magnitude, we have to consider the entire thing in total, and it creates a challenge to understanding and doing the science. I would also argue that this presents an opportunity. So if we can understand energy transfer mechanisms between the various modes, kinetic, chemical, internal energy modes, and exploit them, then it gives us a new opportunity to do a different type of flow control for these very high-speed flows. This is important to the Air Force because the aerodynamic base state really creates the boundary conditions for every other aspect of the vehicle that we would like to design and optimize for high-speed systems. So if the Air Force is going to develop high-speed systems in the future, getting the aero base state right is critical, and my portfolio addresses the underlying scientific challenges of doing that. The reason this is important to the Air Force right now, and it's always been important for the last 60 years, ever since von Karman wrote Towards New Horizons, high speed has been a critical part of the Air Force plan and vision. But lately, as we look at the pivot to the Pacific and ideas that we want to operate in this anti-access, anti-area denial environment, we're considering and so let's use the United States as a reference map here because we're all familiar with the scales we're talking about. If I'm in Arlington, Virginia, and I decide I want to deliver something using a conventional system, in about 15 minutes, shown by the red circle there, I can cover most of the Mid-Atlantic region. But at Mach 6, I can get to the Rockies, and at Mach 9, I can get to the West Coast. So if we switch gears and think about, I have a franchise, say I'm delivering pizzas, want to do something different, using conventional speech, conventional systems, I have to have 120 franchises to cover the same area that I can cover at Mach 9. It's about a factor of 50 increase at Mach 5. The point being is, it doesn't matter how expensive the weapon is. If I want to hold an area covered for a specific amount of time, I have a leverage, area covered per time. The range gives me that added benefit, and economy of scale allows me to cover a much greater area there. So I essentially can reduce all the infrastructure, all the requirements, all the security things. One or two very secure delivery centers may be much better off economically than, say, 50 or 120 at lesser speeds. So hopefully what we've done so far is kind of set the foundation for the talk. We're addressing challenging science, and it's relevant critical needs of the Air Force. For the rest of the talk, I'm going to do a couple things. First, we're going to talk about the summary of the research thrust in the portfolio. We'll hit the big picture. What's the national picture for high-speed research look like? And then I'll hit some technical highlights and where we're going. What I want you to get out of that is that we are in a unique position. The way the big picture is, our portfolio has a demand on it. We have a mandate to be transformational and to have leadership in the community. We are, in fact, leading transformation in certain areas. We're organizing the community, and we're establishing new research opportunities for the community as well. Until last year, this portfolio was a single entity that comprised what I'm going to tell you today and the portfolio that Pon Reagan-Salmi briefed on Monday. When I became department chair last year, we split the portfolio into two components. I now manage Aerothermodynamics. Pon manages turbulence and transition. We had 4 research areas that I would have briefed in years past. Today I'm going to focus on the 2 that remain in my portfolio, non-equilibrium flows and shock interactions. And let's get to both 2 areas right now. So the challenge with rate-dependent non-equilibrium flows is that we have a really hard time simulating them. So if we look at, this is an example of a double cone simulation from about a decade ago. Candler did this as part of RTO activity. You can see the image of the flow field on the left, and then we have simulations for nitrogen and air at increasing enthalpy. As the enthalpy increases, the chemical complexity we have to reproduce increases as well. What you see is for the nitrogen case, we have very good agreement between the experimental data and the simulation results. As the chemical complexity increases, not only does the agreement get worse, but the trends start heading in opposite directions. Given that the numerics, the model, everything else is the same, what we can infer from this is that we need to be able to simulate non-equilibrium rate-dependent chemistry at a far better state than we can right now if we're going to have better simulations of high-speed flows. So we have to reduce uncertainty in both the reactions and the rates. Ideally, you would like to know enough where we can exploit this transient phenomena. We have some partners we work with, including NASA, Sandia, and in the international community, we do a lot of work with the NATO RTO group. Shock interactions, you can't avoid them for high-speed flows. Every high-speed system we have has a shock interaction in it of some type or another. The challenge is, and if we just look at the zoom in here, it creates a lot of distortion, a lot of local loads on these types of systems, and we can't predict them. So you may have a local separation phenomena, a local reattachment phenomena, where you suddenly produce a significant heat transfer increase or a surface load of 150 decibels into the structure. And we simply are challenged to predict those at times. So we want to start improving that. We have to understand where the kinetic energy goes in the turbulent spectrum, particularly when it's processed through a strong shock interaction, where the unsteadiness comes from, and eventually we're going to move towards 3-dimensional flows. In fact, that's where I think our leadership is going to, leadership within the portfolio, our contribution is going to be taking the community into new directions to look at these highly distorted 3-dimensional flows. This is the big picture for hypersonics. Now, I want to put a brief commentary on here. This is not the hypersonics portfolio. When I took over this portfolio 13 years ago, it was in fact called unsteady aerodynamics and hypersonics, but hypersonics is technology and not a science. So there are 3 portfolios at AFOSR that actually address the critical science relevant to hypersonic technologies. It's useful, I think, though, to look at budgetary investments to give us a sense of what we're dealing with here and where our mandate comes from. So the nation invests several $billion every couple of years in the development and maturation of high-speed hypersonic systems. Every time we fly a flight demonstration, we're looking at a $100 to $400 million investment, and those are typically developed, analysis done on those based on decades-old tried and true engineering tools. And we wonder why these things sometimes fail or fall out of the air. If you compare the foundational research investment, the 6-1 national push to feed the pipeline that's going to give us better tools, right now we're putting about $12 million a year nationally into these types of things. And my portfolio is just one portion of that. So the challenge is that, there's very few investments out there. If we're going to have an impact, if we're going to transform what's going on, we can't miss. We have to be both transformative, we also have to be risky. We have to transform current practice, really organize the research community, and create innovative new ideas and research opportunities to take the scientific community in the direction we need to go. Over the last couple of years, we've been very effective in being a leader in the community. We were the source, in fact, developed the HiFire program, which is now, I think, the largest collaborative scientific investment in aerospace between the United States and Australia. We've done a lot of work in leading NATO activities. We've worked with ONR on jet noise development work. Earlier in the week, you heard from Pon from the National Hypersonic Foundational Research Plan, or National Hypersonic Science Centers. Today, I'll just focus on where we're going in the future, a new paradigm for understanding high-speed flows. How do we understand energy transfer mechanisms? Now, it says summary of accomplishments. That's probably a legacy of when I was thinking about how we're going to talk to the SAB. What I really want to talk about is a kind of summary of trends and directions. This is where we are going as a portfolio. I'll talk a little bit about the development of gas surface interaction simulations. We've been thinking about that since about 2003. In fact, I showed the dates, so since we've been developing these things, I would note that all of these things result from a long-term strategic vision in the portfolio. We set out to do something and have kind of stuck to our guns over a few years, and some of the progress we've made that we reported earlier in the week results from that long-term vision. But we'll talk about how we're organizing a multidisciplinary research community to look at gas surface interactions. We're trying to create new directions in terms of energy transfer, and we're trying to transform what we currently do in the analysis of inlets by looking at three-dimensional shock boundary interactions. So for gas surface interactions, we've had a vision for a long time. This goes back to when Joan Fuller and I were talking about how to merge aerothermodynamics and high-temperature materials research. And so we started with a series of workshops called the ATM workshops for aerothermal materials, not as a cash machine. Some of our PIs wished it had been the latter. But we started setting directions for that and identifying things that we needed to be addressed. What followed on after that was a joint set of workshops that we co-sponsored and developed with NASA and Sandia. It's now the ablation workshops. And the interesting thing that came out of that is originally ablation work was all ITAR restricted. And we eventually did one of the very first public release open workshops on the fundamental science issues of ITAR. And in 2012, we handed it off to academia. And in fact, in April, the 6th ablation workshop is being organized by faculty members at the University of Illinois and University of Kentucky. And for the first time, AFOSR and NASA have nothing to do with it. We've handed it to the community. They're going on their own. Last year, we had a spin-off out of this activity, a Gordon Research Conference on Atmospheric Reentry Physics. But one of the other key things that came out of this was we understood that there was a need for a Murray topic on fundamental processes in high temperature, high speed flows. And so in fact, working with the chemistry community and materials community, we set up that Murray. I would note that my portfolio has really benefited from interactions with the program managers who do high speed materials and chemistry. So Ali and Mike, we've had tremendous interactions. We've benefited from the expertise their PIs have. What our Murray is doing is looking at the kind of the full spectrum scale up from fundamental quantum simulations all the way to CFD, continuum flow simulations for high-speed vehicles. Starting at the quantum level, we're computing potential energy surfaces that would give us the intermolecular potential. Then we apply those in molecular dynamics simulations, and want to scale up then at the mesoscale and finally get to the CFD, continuum model simulations. And all through the process, we have companion experiments that are actually validating and providing guidance along the way that we're actually, doing, that the physics is being done correctly. Now, one of the highlights I'd like to show is from one of the members of that. We also sponsored him under YIP. This is Tom Schwarzentuber from the University of Minnesota. What Tom has done is use these quantum potential energy surfaces to inform molecular dynamics simulations, and then incorporated that into some of the CFD methods we use for particle simulation, something called direct simulation Monte Carlo. So now, in the past, where we would model potential energy, we'd model various reaction rates. Using these potential energy surfaces, Tom can actually use that as the only modeled input that goes into the computation of a strong shock wave. So this is a classic case of a shock tube. Shock balances off the reflective wall, moves back, creates a very elevated temperature condition at the end. The yellow dots are nitrogen molecules. The green dots are nitrogen atoms. And what you can see is he's plotted on top of that the various internal energy states. We have for the first time basically a direct molecular simulation, the particle analog to a continuum direct numerical simulation, essentially a model-free simulation of the transient internal energy states associated with a shock wave. And we're really excited about where that's going. This is a simulation of about 7 million particles. One of the things Tom did to improve his simulation capabilities is also scaling up the way he do simulations. So he took molecular dynamics, looked at it and said, some of my DSMC methods would apply to making these simulations better. So he came up with an improved version of this. And the thing is, a lot of times in simulations, they'll compute a particle and it bounces off something, they have a collision, and it kind of sits there. What Tom said is, I can redo the algorithm, I can do the numerics and accelerate all that time between collisions, therefore focus most of my computational time on the collision part itself. And he's able to speed up the process and have much larger simulations than we previously would have had. As a result, we're looking at now applying this method to things around relevant flows, such as the nose tip here, embedding billions of particle collisions within an actual flow field simulation. In applying this in some of the preliminary work, though, we've had some very interesting discoveries. One of the things is that traditionally we would model the rotational excitation or de-excitation, the rotational characteristic time, as kind of being one representative number. Tom's simulations have indicated that, in fact, the excitation state for rotational states is a much faster process than the de-excitation state. And in fact, there are several associated timescales involved, one for excitation, one for relaxation, excuse me. The two are separate, and modeling them with just one representative timescale is probably not the most accurate approach. We also have international and military partners involved with this. This is actually a joint effort between the University of Queensland and AFIT. We're sponsoring the AFIT part of this. Work's being done by Captain Chris Alva, who I've known for a long time, and I expect to have a real impact on where we go in this field in the future. So at the University of Queensland, they're using an expansion tunnel to create a very high enthalpy hypervelocity flow over a heated carbon piece that represents a nose tip. They're making spectroscopy measurements and looking at the radiation emission from the CN compound formed as part of that interaction. What they're doing at AFIT then is using some of the methods developed in the portfolio to look at that radiation, model it, and on the lower right-hand side here, you can see that the actual simulations are agreeing quite well with the experimental data. We're excited about this, and again, I think it's a great international component within the portfolio. Now let's move on to another topic. Our new research direction is looking at energy transfer. So historically, this portfolio has always been considered the hypersonics portfolio. And that's a good thing, it's relevant, but it's not all we do. A lot of the science we do is relevant to other things. We wanted to try and rebrand ourselves to think about what's the science we're actually doing. And so we've been emphasizing this idea that we address fundamental mechanisms of energy transfer. That allows us to start thinking about other things. I would say that the gas surface interaction in a more generic sense is something that we can really contribute to, various types of thermal management and energy phenomena. But it's also positioned us to try and interact in a more positive way with the other portfolios within AFOSR. And we've been very fortunate to be the recipient of one of our basic research initiatives that has really fostered some integrated work with 4 other portfolios within AFOSR, and we've benefited from it. I'm going to talk now about a couple of the BRI efforts. I would note that one of the key things out of this BRI is that a lot of my PIs are now doing work as PIs in other portfolios within AFOSR. I consider this missionary work. So my PIs are taking ideas from my portfolio, awareness of what the challenges are out to chemistry, the plasma dynamics portfolio, other places, and they're going to come back later on with new techniques, new methods, new insights, and we'll apply to things that are of interest to my portfolio. So I'm very excited about this tech transfer, this exchange of hostages, if you will, to create some new ideas. So this is work under the BRI done at Texas A&M. It's led by one of our YIP type guys, Diego Donges, but when he's got the department chair and a couple other senior guys, it's a good team. Bill Haas, you heard Mike's work this morning and talked about his work. So asking the question, if you look at the characteristic turbulent kinetic energy spectrum, can we align relaxation times from different internal energy states? It's color-coded here. You can see vibrational relaxation at one end, rotational, translational, electronic at the other. Can we shape the turbulent kinetic energy spectrum by lining up strategically the characteristic timescales of the fluctuations with different relaxation rates? We're about a year into this. There's a lot of work yet to be done. It's looking very promising. But here's what these guys are doing. So they're creating, it's a combination of experimental and direct numerical simulation work. On the experiment side, they're creating these grids of very well-controlled turbulence. You take a flow field, you seed a couple of molecules into it. One of them is SF6. The others I can never remember because I'm not a chemist. But there's some molecules you introduce, and depending on which particle or which trace component of gas you introduce into the flow, you can photodissociate it with the laser. And then based on your gas choice, you can create pure rotational, pure vibrational, or pure translational energy in a very regularly spaced, spatially oriented turbulence grid. So we're now creating well-defined turbulence of a very specified type in terms of the internal energy state. And then we can watch how it relaxes over time with some of the diagnostic methods these guys are employing. And in parallel, Professor Donzis is doing simulations of these types of flows using very large-scale direct numerical simulations. So we're looking both from a modeling and an experimental side at the detailed energy reactions that are occurring. One of the interesting things that also is at play here is that the Texas A&M guys have a diagnostic method that's kind of based on the same type of effect. So the Venom technique is a vibrationally excited nitric oxide monitoring. What they do is they seed nitrogen dioxide into the flow field, use that same photodissociation process to create excited state nitric oxide. That nitric oxide, then they can interrogate using planar laser-induced fluorescence. And then the bottom line in all this is that using a multi-plane approach, they can make simultaneous measurements of the velocity, temperature, density, and pressure fluctuations. And if you look at some of the things we want to model in turbulent flows, being able to look at all those things simultaneously allows us to look at some of the turbulent kinetic energy and stress rates and other things that have been a challenge to measure experimentally in the past. So this provides us a great opportunity to look at some new insight into the physics of turbulent flows. Now, this is the other BRI I like to talk about. This is work done at the University of Texas, led by Phil Varghese, including Noel Clements and Venkat Raman. It's very qualitatively similar to what we've talked about in the last couple of highlights, but this is different because it's looking at supersonic combustion and the role of non-equilibrium processes in that combustion process. So they've got a new supersonic burner facility, and they're applying state-of-the-art spectroscopic diagnostics to that. But they also have a very interesting numerical approach. So earlier we talked about Schwarzentuber's work and how he has potential energy surfaces that have been developed, and then he uses those as the only modeled input in his simulation. What they're doing at Texas is a little different, is they're actually computing the potential energy surface on the fly. So using a table lookup and interpolation, they're doing their simulation, and they actually compute the potential energy surface using this ISPESR process. It's basically an integrated part of the potential energy surface within the simulation itself. What's shown in the image here on the I guess your left is the error in one of their potential energy surface calculations, and basically they can, depending on how much computational power they put in, they can drive it down just about any level they want to specify. And it's interesting when they started employing this in some very large-scale simulations. So the direct numerical simulation of a non-equilibrium hot jet is shown here. And we think this is the first, you always hesitate to say this is the first of this kind, but we're not aware of much similar work like this out there. So this is a DNS of a supersonic reacting jet, including the thermal non-equilibrium inside that. It's about, I don't know what 10 to the 9 is, like, 10, like a billion? I don't know. 10 to the 9th, it's been a long week, it's Friday afternoon. There's about 10 to the 9th different degrees of freedom in this simulation. It's a very complex thing, and we're interested to see how it's going to turn out. Okay, so the other area I want to talk about is shock interactions. Again, they're ubiquitous, they're everywhere, they are a pacing issue for high-speed flows. Now, what's interesting is they're of interest to a lot of things as well, but looking at our icon of a high-speed system here, they create extreme heat transfer on the surface. They can create incredible acoustic loads that have to be handled in the structure of that surface. They can cause distortion and unstart in the inlet. That circle there with the green blobs in the middle is what happens to the inlet of an axisymmetric configuration when you've got it off-axis angle attack. So that's what happens when a shock interaction occurs inside a kind of round inlet, and you can see those green blobs are actually the low momentum boundary layer fluid that's going to go sucking into the engine and potentially cause unstart. It's important, understanding this type of phenomenon is a pacing issue for development of high-speed propulsion. Interestingly, those directed energy guys are interested in this as well. So if you're looking at a directed energy gas laser and you want to incorporate it into an aircraft, turns out the diffuser length is a really important part of that. I can't have 50, 75 feet of diffuser to slow down the gas that I've used for the laser. So those guys actually rely on a very well-controlled shock boundary layer interaction to minimize their diffuser length. So beyond aerodynamics, there's a lot of gas dynamic potential things that can occur that shock interactions are part of. I think the directed energy one is very interesting because it's a very low Reynolds number, non-equilibrium process, and I think we could take some of the methods we've been developing and really attack that problem. There's about 5 different groups in AFRL that are interested in this as well, and we've been working to try and coordinate and ensure that they're all talking to each other. So our opportunity is to utilize some of these emerging capabilities to drive this in a direction. So the last many decades, most of the work we've done has been in two-dimensional interactions. We've got an icon from Rosetta's and Visbal that's showing this two-dimensional interaction here. Where we want to go and where I think the portfolio needs to take us is into three-dimensional interactions, which you can see are qualitatively much, much different. And we'll talk a little more about that, but the first thing I want to do is review where we've gone with 2D stuff in the past. So this is a little look back. In fact, I brought a vintage highlight out from 2004. This is Murray that started then, so I'd say I probably showed this between 2007, 2009. This is work at Dave Dahling and Lowell Clemens, University of Texas. You can see their two-dimensional ramp-generated interaction there on the upper left-hand corner. What we're looking at is a couple of images of the flow, the turbulent flow going into that interaction. What you see, that white area on the right-hand side is the shock wave ripple structure in a span-wise direction. So notionally, this is a two-dimensional interaction. It should be kind of span-wise symmetric, except these hot streaks in the boundary layer, these long, coherent, organized streaks are actually driving this span-wise rippling. We've got this span-wise variation, and the dynamics of that. And this is images from their wind tunnel test showing these long, coherent streaks in the boundary layer. They indicate that this actually drives a span-wise unsteadiness effect. And now that unsteadiness can be, we can generate in two-dimensional interactions, again, acoustic loads of 140, 150 decibels. That's important. We have to take into account for those things. But this is interesting. Pino Martin out of the University of Maryland did some direct numerical simulation for us, looking at these phenomena as well. She sampled her, and she looked at the development of hairpin vortices that would contribute to the growth of these superstructures. One nice thing she did was she actually sampled her simulations analogously to the way we would do experimental work. So you had an apples-to-apples comparison. Here's what the experimental guys got, and she sampled the DNS in the same manner, so you can compare them both. And what you see is that, in fact, she sees some low frequency unsteadiness as well. Again, all looking at these two-dimensional interactions. High Fire Flight 1 gave us flight data in this type of phenomenon. So we never understood whether these long structures, this fundamental unsteadiness, came from a wind tunnel artifact or whether it was something we actually had to worry about in flight. So one of the things we wanted to get out of High Fire Flight 1 was, what does the unsteady nature of shock interactions look like? And so the data from High Fire Flight 1 is shown right here. And I've shown the High Fire flight data and then data from Dahling and Murphy from probably around 1990 would be my guess, around then. Qualitatively, the same unsteady nature appears in both. So we know this is a phenomenon that occurs on flight vehicles. It's not a wind tunnel artifact. We need to understand a little more. There's been a lot of work trying to understand this. In fact, the community has focused on this for the last several decades. So why are we going in a different direction? And here's why. We're not going to hang square inlets on a box underneath future systems. Future systems are going to look like this. They're going to have actually symmetric inlets. They're going to be integrated in some fashion. They're going to give us highly three-dimensional flows. And so all the dynamics, everything I've talked about with these nice, low frequency unsteadiness, there's a recirculation bubble in there, and a lot of people have been looking at how does that bubble dynamics work? How does that, guess what? As soon as I add any sweep, that entire recirculation goes away. I open up the end of that bubble, it's no longer confined, and I've got this vortex screaming along the surface, as you can see over here. The fundamental dynamics of this interaction are going to change remarkably as soon as we go to 3 dimensions. And so we're taking the community in that direction. It's going to be hard. Right now, The only thing we can do for some of these three-dimensional flows is Reynolds average Navier-Stokes, which is any of you guys, any of our scientists know that's not what we want to do. We've got a lot of modeled terms in there. You know, turbulence models always give you problems, but that's what we can do right now for very large three-dimensional flows of this type. Our goal is to start moving this to the right here into more and more high fidelity, looking at first directed detached eddy simulations, LES. I don't know if we'll get to DNS, under very, very low Reynolds number, very controlled conditions possibly. And we've got to start looking at more of the high fidelity simulations of this type of flow, and we want to start taking the community in that direction. So let's summarize real quick. There's a very strong application pull for what we do in this portfolio. The Air Force is interested in this. It's needed. We've got a very limited resources. On a national level, we are the program addressing things in this area. We partner with other things, but as far as the DoD is concerned, we're it. But there's broad potential impact. And so I would argue that we have a portfolio mandate. We must transform current practice. We have to organize a research community, and we need to create new research opportunities. And the three things I've shown today, I hope address that. Going kind of in reverse order. We're trying to transform the way we look at high-speed inlets and shock interactions by focusing on three-dimensional aspects. The work we're doing in gas surface interactions and really bringing together the chemistry, materials, and fluid dynamics community is innovative. We're looking at integrating molecular dynamics simulations. I would argue that most of us would have predicted this. We would have seen that coming. That's the next logical step. It's hard, we're at the forefront, but most of us would have said, yes, that's the next logical step. I would argue that what we're doing in energy transfer is unprecedented. And I haven't talked about some of the things that have come out of the portfolio. I think PON has some things in his portfolio in terms of transition control with kinetic energy to internal energy state transfer, but exploiting the energy transfer between internal energy, chemical, and kinetic energy state for the purposes of flow control at a macroscopic scale is something that I think we have not really thought about, and I would argue that's an unprecedented direction. So again, we have a balance of things in the portfolio, and I'm really excited about where we're going with it. I want to wrap up with giving credit to the guys who deserve the most credit for the device, and this is our PIs. I hope a lot of my PIs are watching this because I'm very proud of all their contributions. This is a list of just some of the things our current PIs are doing. We've had some alumni that have gone on to some significant things. A number of tech transitions 2 years ago now, so we're a little year out of date, but AIAA gives 3 summer technical awards in the fluid dynamics community. 2 years ago, we got half of them. We had the trifecta. Guys in my portfolio receiving prestigious national awards. I was really proud of that. Every one of my PIs is a leader. They're exceptional at what they do, and I'm really proud to have them in the portfolio. So with that, let's summarize. We're addressing challenging science that is critical to Air Force future plans. We have a unique national role. We're trying to lead transformation in terms of shock interactions. We're organizing the community and what we're doing in gas surface interactions. And we're looking at some really interesting, I think, unprecedented new research directions in terms of energy transfer. And I appreciate your time today. I'd be happy to answer any questions. Or I could turn my exit music on.
John, I have a question for you.
Yes.
When I see transformational and 3D shocks, I think, oh my God, it's deja vu all over again.
Mm-hmm.
I started in graduate school back in the late 80s. I mean, that's exactly what was going on in those facilities, the gas dynamics facilities that had the capability to do that. So Penn State, Texas, Princeton, they were doing these 3D interactions. In fact, it's kind of a little bit crazy to see these pictures again. So what's transformational now? I mean, why did the focus shift to 2D, and now you're saying, okay, it's coming back to 3D? I mean, is there some sort of continuity there that we can
Sure.
that we can sort of draw a line, between these things and say this is why we're doing this?
Sure. Let me go ahead and repeat the question for those folks. So what Doug brought up is, in fact, three-dimensional shock boundary interactions is nothing new. Some of the images I've shown to motivate what we're doing are things that I did in 2000. So Doug's question is, what's transformational, what's new about that? And my argument's going to be, we now have the tools to actually look at the dynamics. So in 2000, Dave Dolling, who was my master's thesis advisor, wrote a paper called 50 Years of Shock Boundary Interactions, and this was 10 years ago, okay? The thing is, it's a very, this has been a pacing issue for high-speed flows for a long time. We've gone in fits and starts. Through the 70s, 80s, and 90s, we did a lot of mean flow measurements. We would do surface flow viz. We'd look at coolite, so it's unsteady pressure measurements. I would say that I probably took the last three-dimensional unsteady pressure measurements for a swept interaction around 1992. I'm
close. I just he did something similar.
Okay. So around, but I was part of the last generation that did this. Okay. Then we started looking at two-dimensional interactions almost exclusively, and it just became this idea. Okay, we have to understand the unsteadiness. We have to understand where the source is coming from, and so things went kind of dormant for a while. In fact, the very first workshop I had as a program manager coming to AFOSR in 2002 is how are we going to reinvigorate shock boundary interactions. Had a bunch of people come in, and we had some ideas, and we did some stuff. That's when we first started funding Professor Martin in Maryland. We did a couple other things, and again, we started looking at two-dimensional interactions. What's changed? Okay, this is a problem. It's not going to go away. We've known about it for a long time. We have the diagnostic capabilities now. The Venom tool I was talking about earlier, we've got things like we've got megahertz pulse burst lasers now that allow us to interrogate these types of interactions at very high rep rates. And the numerical tools are maturing to the point where I believe we can start moving off of the RANS simulations towards LES. And so now when we get to LES, when we get to better diagnostics, I think we have a chance to start unlocking the critical dynamics that occur in these interactions. Previously, our analogy would have been what the materials community does in terms of cook and look or shake and bake. We're going to go out, we're going to take some data, we're going to look at it, and we're going to try and infer some things. I really believe that now we have the diagnostics and the numerical simulation capabilities to start popping the hood on these interactions and looking at them in scientifically respectable detail. We can start to look at the critical dynamics, and I think we're finally at the stage where we can start to get into the details of what's going on there. Did that answer your question? Yeah. Okay. Dr. Manson.
You mentioned that you can look at some flowing gas lasers with the kind of technology you're doing. The emphasis in high-power lasers these days is much more in solid state and fiber. So what's the relevance of the Air Force focusing there?
And I think in terms of direct relevance, I mean, I am aware that we've moved away from the gas-powered lasers to solid state. There's one of the reasons we probably couldn't make the gas work on. Again, I'm making this up as we go, but there's details there. So it's not the Air Force direct relevance to the laser in terms of understanding and improving things in the future. We may come back to gas in the future. There may be other applications. To my knowledge, we are. This is an area that I want to take the portfolio in. So right now, I'm an expert on what we're doing in Aero. I want to take the portfolio into things like gas lasers, into optics, other things. And that is, I think, one motivating thing, but it remains to be seen.
John?
Yes, Pan.
You mentioned about diagnostics and simulation. Mm-hmm. And in your past 10, 15 years of exposure and steering this science into real exotic directions, what is your impression about the current computational capabilities and the demand for new instrumentation in these two areas? Do you see help towards improvement, or we are still churning spinning the wheel by garbage in, garbage out? The computers will crank any billion numbers you give it to them. Sure. But are we progressing in the right direction?
Okay, so Pon's question had to do with are we heading in the right direction with regard to numerics and diagnostics. I think part of what my response to Doug's question in terms of why are we looking at 3D interactions now, we've made a lot of progress, but what needs to be done? So we've had a lot of emphasis on large-scale parallel simulations over the last few years. And I think that's bought us some breathing room in terms of going to very large simulations. But eventually, the real work's going to have to be done in algorithms. So we're going to have to revisit the way we actually simulate the governing equations to ask ourselves, are there algorithmic improvements that we can look at? One of the things I didn't show, because it's now actually in your portfolio, Pon, is some work out of the University of Minnesota looking at kinetic energy preserving schemes. So the idea that you can take a central differencing scheme And okay, background for everybody. If you want to compute a high-speed flow, most of what we do is upwind schemes right now because they are, helps you capture the shocks better. But they're incredibly dissipative, and as a result, any type of kinetic energy that you're going to try and capture gets dissipated in artificial dissipation very quickly. What the guys in Minnesota are doing are going to a central difference, second order, but with some modifications in the way they recombine the fluxes in those second order differences to give them a kinetic energy preserving capability. So now for a second order investment in terms of grid size and simulation, and you have to do some stuff with the shockwave capturing still, but now they can capture and maintain kinetic energy at a much larger scale. Again, digging into the numerics, popping the hood, going back and revisiting some of the things that have gotten us this far, improve our numerical methods, I think is what's going to be required to really resolve where we're going. And as far as diagnostics, I mentioned things like the megahertz pulse rate laser being able to capture, at a megahertz sampling rate, say 20 or 30 snapshots of the flow in a row. Some of our spectroscopic measurements. There's a lot of interesting things we can do. So, and I think there's a lot of emerging stuff there. As far as gas surface interactions, we need resolved spectroscopic data near the surface of that gas surface interaction. We can understand what the species are that are coming off that surface in these transient processes. I got all day. Who else wants to? Okay. And I think we're done now. So thank you very much. Appreciate your time. On behalf of the Energy, Power, and Propulsion Sciences Division, thank you for participating in Spring Review today. And I think on behalf of Dr. Carrick and Dr. Madsen, thank you for being part of Spring Review. Have a good afternoon.